got some past exam questions here on amino acids, amides and chirality. It's actually the second batch of these questions that I've done. If you haven't tried the first lot, then the link to that video should be on the screen now. So basically with all of these, the link to the questions is in the description of the video. So click on the link, download the questions, have a go, and then play on when you're ready for the answers. Okay, so I'm going to go through the answers slightly differently to the norm. So normally everything would be blank and I would sort of fill in the answers as I'm talking, and that takes a long time to do. I haven't mastered the knack of talking and writing at the same time. So I'm going to give this a go. I would love to know what you think of this style, because if this is okay with everybody, I can do these much quicker than the other way that I've been doing them. So the answers are already there. I'm just going to talk through what I've done, some little clues, some little tips that you can do, and then hopefully that'll be okay for everybody. Okay, so the first question, we've got to circle the two chiral carbon atoms in aspartame. So basically we're looking for two carbon atoms that have four different atoms or groups of atoms attached. So this one here has got the NH2 group, the H, this group here, and all of that there. So that's four different groups, so that's a chiral carbon. And likewise this one here, hydrogen, this thing with the benzene ring on the end, this here, and then all of that. So there are your two chiral carbons. The four functional groups other than the benzene ring in this molecule, so you can see I've done them by colour code. So there's an ester group there. We've got a carboxylic acid group over here. We've got an amine group here. It's actually a primary amine, that, but the mark scheme doesn't specify the need for primary. And what we've got here, and a common mistake here I would see would be ketone. Because you've got an N directly bonded to that C double bond O, it's actually an amide. And this is actually a secondary amide because the nitrogen's got two carbons bonded to it. But again, the secondary wasn't essential. So ester, carboxylic acid, amine and amide. To get the 2 marks, you need to get all 4 right. If you got 3 right, you only got 1 mark, I'm afraid. Question 2 is about this compound MEA, which can be oxidized to form an alpha amino acid. So the first part of the question, we've just got to define alpha amino acid. So that's an amino acid where the NH2 and the COOH groups are bonded to the same carbon atom. And the next thing I'm going to do is write an equation for the oxidation of MEA to an alpha amino acid. So what I've done at the bottom here, there's MEA sort of in a displayed formula format. So it's easy to see what's going to need to happen. So we've got a primary alcohol group here, and what we've got to do is turn that into a carboxylic acid group. So primary alcohols need to be oxidized twice. So we need 2 moles of oxidizing agent to get it to the carboxylic acid, and we also get a water molecule as well. Remember, water is only produced when you go from the primary alcohol to the aldehyde in that first oxidation. Going from the aldehyde to the carboxylic acid doesn't make any more water. So there's only one water molecule needed in that equation. Question 3, isomers F and G are hydroxyamines. So you'll see I've noticed up there, that means they've got an OH and an NH2. And I would always encourage my students, as you're reading through information, especially stuff that you may not have seen before. So hydroxyamines aren't on the syllabus, but obviously the examiner's expecting you to be able to work out what it is. Hydroxy, OH, amine, NH2, it could be NH even if it was a secondary amine. And we've got this molecular formula. So we're told that isomer F can be dehydrated to form the cyclic compound, this thing here. So what I've done is, you can see here I've drawn up a molecule that would be able to become a cyclic compound from the loss of water. So if we've got an NH2 group at one end of this carbon chain and a CH2OH group at the other end of the carbon chain, if you lasso out water, take out the H and the OH, you can actually connect these, the carbon to the nitrogen, and you can create a ring. So isomer F has to be that. Isomer G now, so that's got to have 2 chiral centres. So again, we need to sort of reposition the atoms, the groups of atoms. So we've got 2 carbon atoms with 4 different groups attached. So this carbon here, we've got 1, so the H, 1 group, NH2, 2 groups, CH3, another group, and then that's the 4th group. And then this carbon here, we've got no H group and H, CH3, and then that group there. Moving on to question 4 about penicillamine, we've got to explain why it's described as an alpha amino acid. We've kind of already had this question before, but just to show you that, you know, they can ask the same thing in slightly different ways. Again, we're just saying that the COH and the NH2 groups are bonded to the same carbon atom. Next bit, dilute aqueous acid is added to an aqueous solution of penicillamine. Draw the structure of the ion that forms. You can see I've written in red there. The H plus ion from the acid is going to be accepted by the lone pair on that nitrogen of the NH2 group. So if you've got an H plus up there, you're going to get a dative covalent bond being formed between the nitrogen and the H plus ion. That's not required for this question, but it's just a little bit of extra theory there for you. So obviously the product of that, all it's changing is the NH2 is changing into an NH3 plus ion. Next question, all we've got to do is draw a 3D diagram to show the structure of the other optical isomer. So essentially we're drawing the mirror image of this. So the dashed bond needs to be pointing sort of towards the mirror like that. Obviously the H is on there because it's on the dashed bond on that one. The wedge has the COH on, and then the NH2 group's on this side of the molecule, and obviously that's still sticking straight up. So the 3D bit just means that we've got to show this dashed line and the wedge. Next part of the question, slightly tricky in the sense that we're being told some brand new information about a thiol group. It's not on the specification, so we've got to digest that information and then come up with an answer. So quite tricky because of that. So we're told that the SH and NH2 groups in penicillamine react with halogenoalkanes by nucleophilic substitution. So penicillamine reacts with a dihalogenoalkane to form compound shown below. So you can hopefully you can see what I've done here. I'm just focusing on that's where the change is. So I've just drawn the carbon with the SH on and the carbon with the NH2 group on, which is what we had to start with. Now if we want to get this green group on, we're going to need dichloro version of that, or it could be a dibromo if you wanted to. I would tend to go for the chloro version. I don't know why, but there you go. So you can see the substitution is going to take place because the chlorine and the hydrogen are going to combine together to form HCl molecules, and then obviously we can put that green part in position there, which is exactly what you've got there. So to answer the question, the dihalogenoalkane is that. Obviously it could be a dibromo version if you wanted. Question number 5, draw the displayed formula for N-ethyl propanamide. So what I've done is drawn up the formula for propanamide. It's a primary amide. So I've got that C double bond or NH2 group on 3 carbons essentially. And N-ethyl just means that we've got an ethyl group on the N of the propanamide molecule. So it would look like that, and that's obviously clearly shown the amide functional group. You don't have to do what I've done there, where the the C double bond is on one side and that's on the other side, because obviously this bond can freely rotate anyway. It's a sigma bond. So if you've drawn the NH like that way on, that's fine as well. Question number 6, what's the number of chiral centers in the molecule below? So the answer was 6. I'll just explain one of them. I'll go for that one there. So we're looking for carbons basically with 4 different atoms or groups of atoms attached. So this carbon here has got a methyl group, and then it's got a carbon down there with this on. It's a carbon up there with different stuff directly attached to it, which makes these carbons different from each other. And obviously that carbon there has got a CH2 on it, and then the C double bond and so on. So 6 altogether. And the final question's about serine. So we're told that serine can react with the alpha amino acid glycine. We're given the structure of both amino acids to form 3 different organic products, but they've all got the same molecular formula. Draw the structures of the 3 organic products that can be formed. So what I've done here is I've drawn out serine and glycine. And just remember that two different alpha amino acids can react with each other because, well, you can see what I've done there. I've put serine first, and then I've put glycine second, and all I'm doing is positioning the alpha amino acids so I'm kind of able to lasso out the water. So you get this condensation reaction. Okay, so that would generate that product, which will have that molecular formula. The next one would be just the other way around. So I've got glycine, then serine. Again, I'm lassoing out the water. And basically all that's happened is the H and the CH2OH groups sort of flip around. And then the final one is, you can see what I've done, hopefully you can see what I've done here. I've got glycine, which has got a carboxylic acid group, can also react with an alcohol group, because we've got an alcohol group in serine in the R group. So again, we can get water produced, and that's going to generate an ester bond, which you've got there. So that would be the third possible organic product. So like I said, that's another way that I can do these questions. It's much quicker. There's very, very little editing to do in that, whereas normally I'm constantly deleting stuff and getting sort of tongue-tied and writing absolute garbage because I can't write and speak at the same time. So please let me know what you think of that style, and if you like it, I hope you do prefer it, because it's so much easier for me to make them and I can really bang them out much more quickly than normal. Okay, right, I'll shut up now and let you have a look at this. Cheers, bye.